Tonight, I want you to start with something small enough that your mind doesn't resist it. Something ordinary. Something you understand without effort. Think about your house. You know how long it takes to walk from one room to another? How far the front door is from the kitchen? How space feels when you cross it with your own body? A typical house is only a few thousand square feet. A distance you can cross in seconds. A space your brain maps effortlessly because it evolved to understand environments like this, spaces measured in steps, in seconds, in familiar motion. Now stretch that scale slightly. A football field is 360 feet long, including the end zone, long enough that walking across it feels deliberate, noticeable, but still manageable. Still within human intuition, a mile extends that further. Over 5,000 feet, something you might walk in 15 or 20 minutes. A distance that feels substantial but still grounded in experience. Your brain handles these scales because they relate directly to movement, to effort, to time you can feel passing. Now expand again. The distance across a large country is thousands of miles, something that requires hours in an airplane, days in a car, and already the meaning of distance begins to shift. You no longer walk across it, you traverse it with machines, and your body stops being the reference. The circumference of Earth is about 900 miles, a number so large that driving around the planet without stopping would take more than 2 weeks. And yet even this planetary scale still belongs to geography, to maps, to something you can imagine wrapping around a globe. But the moment we step beyond Earth, intuition begins to fracture. The moon sits about 855 miles away. Far enough that when humans first traveled there, it took 3 days moving faster than anything most people will ever experience. Even at those speeds, the journey wasn't quick. It was long enough for distance to feel real again, not just as a number, but as a span of time separating two worlds. Then comes the first true break. The distance to the sun is about 93 million miles, and numbers at this scale stop behaving like distances. If you tried to drive there at highway speed without stopping, the trip would take over a century, long enough that generations would pass the journey forward like an inheritance. This is the point where distance stops, meaning space alone, and begins to merge with time. Because nothing we build moves fast enough to cross such gaps within a human lifetime. Light, however, does. Light moves at about 282 miles every second, fast enough that it circles Earth more than 7 times in a single second. Fast enough that when you flip a switch, illumination appears instant. Yet even light needs time to cross the solar system. Sunlight, reaching your eyes, left the sun about 8 minutes ago, meaning you never see the sun as it is now, only as it was minutes in the past. And this subtle delay marks the first hint that the universe is structured not just by distance but by history. To handle distances this large, astronomers use a different unit entirely, the light year. Not a measure of time, but a measure of how far light travels in 1 year. Nearly 6 trillion miles. Suddenly, the nearest star beyond our sun, Proxima Centauri, sits 24 light years away, meaning the light you see tonight began its journey more than 4 years ago, crossing darkness for trillions of miles before reaching you within a sphere 16 light years across. There are only a few dozen stellar systems, and this sparse neighborhood already feels empty compared to anything on Earth. Stars are not packed like cities. They are separated by oceans of nothing so vast that even light takes years to cross them. you begin to realize that what looked crowded in the night sky is actually a projection, points compressed onto a flat dome, hiding distances so enormous that motion between them becomes almost meaningless. At this scale, the familiar idea of traveling from one place to another dissolves, replaced by the quieter realization that space is mostly emptiness, and that even the nearest star is separated from you by a gulf so wide that the fastest thing in nature spends years simply crossing it. Once you accept that even the nearest stars are separated by years of travel at light speed, the next step is realizing those stars are not isolated points scattered randomly through space, but members of something vastly larger that you are already inside. The faint band of light stretching across the night sky is not a cloud, not atmosphere, but the flattened disk of our own galaxy seen edge-on, a structure called the Milky Way, spanning roughly 100,000 light years from one side to the other. Every star you can see with your naked eye belongs to this single system, and yet what you see is only a tiny local patch, because most of the galaxy is too distant for individual stars to stand out. Instead, their combined light blurs into a pale glow, a reminder that you are embedded inside a structure so large that even light needs 100,000 years to cross it. Our solar system sits about 26,000 light years from the galactic center, not near the edge, not at the middle, but somewhere in a spiral arm drifting quietly around the core. The sun is not stationary. It orbits the center of the Milky Way at roughly 500,000 miles per hour, a speed that sounds enormous until you realize how long the path is. One complete orbit takes about 225 to 250 million years, meaning the last time the sun was in its current position, dinosaurs had not yet appeared on Earth, continents looked different, and life itself was still evolving toward forms that would later vanish. Since then, Earth has transformed completely. Species have risen and disappeared, and human civilization has emerged, all during a single galactic year that has not yet finished. Distance at this scale becomes inseparable from deep time, because motion across the galaxy unfolds slower than the entire history of complex life. But the Milky Way is not alone. It belongs to a small gravitational family called the local group, a loose collection of more than 80 galaxies bound together by gravity, drifting through space as a shared system. The three largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, each containing billions or hundreds of billions of stars, each separated by distances, measured not in thousands but in millions of light years. Andromeda lies about 5 million light years away, meaning the light reaching your eyes tonight began its journey long before modern humans existed. When that light left Andromeda, early human ancestors were still evolving on Earth, unaware that their distant future descendants would eventually look up and detect the glow of another galaxy approaching across intergalactic space. The local group itself stretches roughly 10 million light years across a region that sounds enormous until you recognize how sparse it is. Between galaxies, there is mostly emptiness, thin gas, and invisible dark matter shaping motion without emitting light. The Milky Way and Andromeda are slowly moving toward each other, drawn by gravity, and in several billion years they may pass through one another in a slow gravitational encounter that reshapes both galaxies without dramatic stellar collisions. Even this interaction, involving hundreds of billions of stars, unfolds gently because the distances between stars are so vast that galaxies behave more like diffuse swarms than solid objects. As your sense of scale expands, the idea of a fixed cosmic address begins to change. You are no longer on Earth orbiting the sun. You are in a solar system inside a spiral arm, inside a galaxy, inside a small gravitational group, drifting through a region of space so large that entire galaxies appear as faint smudges. The night sky stops being a dome filled with stars and becomes a cross-section of a structure you inhabit, a rotating disk embedded within a wider neighborhood, each level nested inside another. What once looked like isolated lights now resolves into a hierarchy, and the Milky Way itself, immense as it seems, settles into place as just one member of a larger community, suspended in a darkness that extends far beyond the limits of a single galaxy. Once galaxies begin to appear not as isolated islands, but as members of groups like the local group, the next realization is that even these groups are not scattered randomly through space, but arranged in patterns that only become visible when you step far enough back. When astronomers mapped the positions of thousands and then millions of galaxies, they expected something close to uniformity, a gentle statistical smoothing where matter-filled space, more or less evenly at large, scales. Instead, the maps revealed something strikingly different. Galaxies tracing enormous filaments, stretching across hundreds of millions of light years, intersecting in dense nodes, and leaving behind vast empty regions where almost nothing exists. This structure came to be known as the cosmic web, a three-dimensional network spanning the observable universe, where galaxies cluster along strands like beads on invisible threads. The filaments themselves are immense, sometimes hundreds of millions of light years long, composed not only of galaxies but also of diffuse gas and vast halos of dark matter that provide the gravitational framework holding everything together. Where multiple filaments intersect, galaxy clusters form dense regions containing hundreds or thousands of galaxies bound by gravity. Embedded in clouds of gas, heated to tens of millions of degrees, between the filaments lie voids, enormous regions of near emptiness that can span hundreds of millions of light years, containing only a few scattered galaxies drifting in relative isolation. The universe at this scale resembles a sponge or foam, the matter concentrated in thin walls and strands surrounding bubbles of darkness. This pattern did not arise by chance, but emerged from tiny fluctuations in density in the early universe, amplified over billions of years by gravity pulling matter toward slightly denser regions, while emptier areas grew increasingly vacant. As surveys improved and more of the sky was mapped in 3 dimensions, astronomers began identifying structures even larger than individual filaments. In 1989, researchers mapping galaxy distributions discovered a massive sheet of galaxies stretching across their survey region. Later named the CFA, Two Great Wall. Roughly 500 million light years long, it was the first indication that matter in the universe could organize into structures far larger than individual clusters. Then came larger discoveries. The Sloan Great Wall, identified in 2003, extended about 137 billion light years across a scale so large that light itself would need more than 1 billion years to travel from one end to the other. These structures were not solid walls, but complex alignments of clusters and filaments forming elongated regions of higher density within the cosmic web. Additional discoveries followed as observations expanded. The Saraswati supercluster, the South Pole Wall, and other immense formations suggested that the universe's architecture might include structures spanning hundreds of millions or even over 1 billion light years. Each discovery pushed the perceived limits of cosmic structure further outward, challenging the assumption that the universe should appear smooth beyond certain scales. Some candidates for even larger structures emerged from indirect observation, such as the Hercules Corona Borealis Great Wall, inferred from gamma-ray burst distributions and estimated to extend several billion light years. Yet its status remained debated Since the apparent alignment might result from observational bias or separate structures appearing connected along our line of sight, the search for the largest structure, therefore, became not just a matter of size, but of coherence, determining whether distant clusters were physically connected or merely coincidentally aligned. Astronomers began combining redshift surveys, X-ray observations, and gravitational lensing maps to trace how clusters and filaments linked together. These techniques allowed them to move beyond flat sky projections and reconstruct the universe in 3 dimensions, revealing connections invisible in optical images alone. The picture that emerged was increasingly intricate, clusters connected by bridges of hot gas, dark matter filaments stretching between them, and walls forming where multiple strands converged. At this scale, the cosmic web stopped being an abstract idea and became a measurable architecture, with boundaries, intersections, and enormous contiguous regions spanning a significant fraction of the observable universe. The question gradually shifted from whether such structures existed to how large a single connected structure could become before the universe's overall uniformity smoothed everything out. For years, astronomers debated which structure truly held the record for the largest known formation in the universe, because identifying something at these scales is not as simple as drawing a boundary around a cluster of galaxies and calling it a single object. The difficulty lies in determining whether distant clusters are physically connected by gravity and shared matter, or merely aligned along our line of sight by coincidence. Many proposed giants, including enormous walls inferred from gamma-ray bursts, remain controversial for precisely this reason. The universe is vast enough that chance alignments can mimic structure, and without direct evidence of physical connections, claims of extreme size remain uncertain. This is why the discovery of Quipu mattered, not just because of its size, but because it was identified as a coherent structure with measurable links between its components. Quipu takes its name from the ancient Incan system of knotted cords used for recording information. And the analogy is fitting because the structure resembles a network of strands connecting dense knots. Each knot corresponds to a galaxy cluster, itself containing hundreds or thousands of galaxies, while the strands between them are filaments of dark matter and hot gas extending across hundreds of millions of light years. Altogether, Quipu spans roughly 4 billion light years, making it the largest confirmed coherent structure yet identified in the observable universe. Within this network lie 68 galaxy clusters, each a massive gravitational system, collectively forming a structure so vast that light would need more than 1 billion years to cross from one side to the other. What distinguishes Quipu from earlier candidates is the method of detection. Instead of relying only on galaxy positions, astronomers traced X-ray emissions from the extremely hot gas permeating galaxy clusters. This gas, heated to millions of degrees by gravitational collapse, glows in X-rays and reveals connections between clusters that might otherwise appear separate. Bridges of faint X-ray emission indicate matter flowing along filaments, linking clusters into a single system. These observations showed that the clusters in Quipu are not isolated but gravitationally associated. Embedded within a shared dark matter framework, the resulting structure is not a flat wall but a complex three-dimensional network, dense in some regions, sparse in others, with clusters connected by elongated filaments stretching across immense distances. Each cluster within Quipu is already enormous. A typical cluster contains trillions of stars spread across thousands of galaxies, along with vast reservoirs of hot gas and even larger halos of dark matter. When dozens of such clusters become linked, the combined mass reaches staggering levels, estimated at roughly 200 quadrillion times the mass of the Sun. This mass is not concentrated in one place, but distributed across a web of gravitational influence, with each cluster interacting with its neighbors through the filaments, connecting them over billions of years. Matter flows along these filaments, feeding clusters, triggering mergers, and gradually shaping the structure into a coherent whole. Some clusters within Quipu may still be merging, while others formed earlier and now sit embedded in the network, preserving traces of past interactions. The existence of a structure this large raises questions about how the universe evolves at the biggest scales. Cosmological models predict that matter should become roughly uniform when viewed over sufficiently large distances, a principle known as large-scale homogeneity. Quipu approaches the scale where this smoothness is expected to emerge, yet it remains a distinct structure, implying that gravitational clustering can extend farther than once assumed. This does not necessarily contradict current models, but it pushes them toward their limits, forcing careful examination of how density fluctuations in the early universe grew into such a vast arrangement. The structure is also dynamic rather than static, with clusters continuing to drift, merge, and reshape the network over cosmic time, meaning Quipu is not a frozen object but a snapshot of an evolving pattern, stretching across a significant portion of the cosmic web. Seen in this context, Quipu is less like a single object and more like a continent of galaxies, a region where gravity has drawn matter into a continuous arrangement large enough that even the scale of superclusters begins to feel local to understand what a structure 4 billion light years across really means. It helps to imagine moving through it, not as a map or geogram, but as a journey unfolding over time. Picture an impossible spacecraft capable of traveling at the speed of light, positioned at one edge of Quipu and aimed toward the far side. The moment you begin, the scale of the structure resists comprehension because even at light speed, nothing appears crowded. For millions of years, you pass through regions of thin gas and scattered galaxies, the filaments of the cosmic web stretching ahead like faint currents rather than solid pathways. Occasionally a galaxy drifts into view, a spiral of hundreds of billions of stars suspended in darkness, then fades behind you as you continue forward through emptiness. After 10 million years, the first major cluster emerges, a concentration of galaxies spread across millions of light years, embedded in hot gas glowing in X-rays, its gravity binding hundreds of galaxies into a slow, drifting swarm. Crossing a cluster takes millions of years, even at light speed. And while you pass through it, the structure never feels crowded, because the galaxies are separated by enormous distances. Once beyond it, the journey returns to filaments, long strands of matter linking clusters across vast gaps. These filaments contain galaxies and diffuse gas, but their density is so low that motion through them resembles traveling through deep intergalactic night. After 100 million years, you have crossed less than a tenth of Quipu. On Earth, continents would have shifted, mountain ranges risen and eroded, and entire evolutionary lineages appeared and vanished. The time required to traverse a fraction of the structure is long enough for planetary surfaces to change beyond recognition. Continuing forward, clusters appear intermittently, each with its own arrangement of galaxies, each embedded in halos of dark matter, invisible yet shaping motion. The pattern repeats without uniformity. Dense nodes separated by long stretches of emptiness, until the idea of a single object dissolves into a landscape of gravitational regions connected across incomprehensible distances. By the time 500 million years have passed, you are only about a third of the way across. During that span, Earth might experience mass extinctions, new ecosystems, or even complete climatic transformations, The sun itself would slowly brighten, altering planetary conditions, while your journey continues through the same vast structure, cluster after cluster, filament after filament. After 1 billion years, you approach the far side, and the sun would already be noticeably more luminous than when you began. Oceans on Earth might begin evaporating, and the conditions that allowed complex life to flourish could be fading, yet Quipu still stretches ahead. Its final regions still distant even at the fastest possible speed. Finally, after 4 billion years, you exit the far boundary, leaving behind a network of galaxy clusters spanning a significant fraction of cosmic space. The journey illustrates not only the scale of Quipu, but also how distance in the universe becomes inseparable from history. When astronomers observe Quipu, they do not see it as it exists at one moment, because light from different parts takes different amounts of time to reach us. The near edge might appear as it was hundreds of millions of years ago, while the far edge appears even earlier, meaning the structure is observed across a span of cosmic evolution rather than as a single snapshot. In effect, Quipu is seen stretched across time, its components captured at different stages of growth, merging, and motion. This blending of distance and time transforms observation into archaeology. Looking farther into the structure means looking deeper into the past, revealing how clusters evolved and how filaments changed over hundreds of millions of years. The universe at these scales is not simply large, it is layered in history, where every point of light carries information from a different era. Moving across Quipu, whether in imagination or observation, becomes less like crossing space and more like drifting through successive chapters of cosmic time, where the structure itself doubles as a record of how gravity assembled matter over billions of years. To understand how something like Quipu can exist at all, you have to step back to a time when none of these structures had formed, when the universe was nearly uniform, filled with hot plasma and only the faintest variations in density. Shortly after the Big Bang, matter was distributed almost evenly, with tiny fluctuations, perhaps 1 part in 100,000. Barely distinguishable, but critically important. Gravity began working on these small differences, pulling matter towards slightly denser regions, making them denser still, while surrounding areas gradually emptied over hundreds of millions of years. These imbalances amplified, forming the first dark matter halos, invisible concentrations of mass that acted as gravitational wells. Ordinary matter fell into these wells, cooled, and ignited the first stars, which later assembled into primitive galaxies. Dark matter played the central role in this process. Unlike ordinary matter, which interacts through radiation and pressure, dark matter responds primarily to gravity, allowing it to collapse earlier and more efficiently. These early dark matter halos merged over time, forming larger halos capable of hosting groups of galaxies and eventually galaxy clusters. The clusters did not form in isolation, but along preferred directions determined by the original density field. Matter flowed along these directions, creating filaments linking clusters together. Over billions of years, these filaments grew, channeling galaxies and gas into nodes where clusters became increasingly massive. Quipu represents a region where this process extended across unusually large scale, connecting dozens of clusters into a continuous gravitational network. Galaxy clusters themselves are the largest gravitationally bound objects in the universe. Each cluster contains hundreds or thousands of galaxies embedded in a vast halo of dark matter, along with enormous reservoirs of hot gas known as the intracluster medium. This gas, heated by gravitational collapse, reaches temperatures of tens of millions of degrees and emits X-rays, making clusters visible even when individual galaxies are faint. Most of a cluster's mass resides not in stars but in dark matter, which dominates the gravitational potential, while the hot gas contains more mass than all the galaxies combined. Within Quipu, these clusters act as anchor points, their gravitational fields interacting across hundreds of millions of light years, maintaining the coherence of the larger structure. Cluster merges further shape the network. As clusters drift along filament, gravity pulls them toward one another. And when they meet, the collision unfolds over billions of years. Galaxies within each cluster pass through largely unharmed because the distances between them are immense. But the hot gas collides, generating shock waves that heat it further and redistribute matter. Dark matter halos pass through each other more cleanly, continuing to influence motion after the visible components separate. These mergers gradually build larger clusters and reinforce the filaments connecting them, allowing structures like Quipu to assemble through repeated interactions over cosmic time. While gravity builds structure, another force works against it: dark energy, which now dominates the energy content of the universe, drives the accelerating expansion of space. As the universe expands, matter becomes more diluted, and the growth of large structures slows. In the early universe, gravity dominated, allowing filaments and clusters to grow rapidly. As dark energy became more influential, expansion began to counteract gravitational collapse, limiting how large structures could become. Quipu exists near the upper range allowed by this competition, formed during an era when gravity still had enough influence to assemble vast networks, but not enough to continue unlimited growth. Over time, expansion will further weaken the connections between clusters, slowing mergers and gradually isolating structures within the cosmic web. The formation of Quipu, therefore, reflects a balance between initial density fluctuations, dark matter scaffolding, gravitational attraction, and cosmic expansion. Tiny variations in the early universe evolved into filaments. Filaments fed clusters. Clusters merged into networks, and expansion gradually slowed the process. The result is not a static object, but a moment in a long evolution, shaped by forces acting across billions of years, where gravity assembled matter into one of the largest coherent patterns the universe has produced before expansion began to pull everything apart. When you step back from the details of clusters, filaments, and dark matter, Quipu becomes more than a measurement of size. It becomes a shift in perspective about how the universe is organized and where we exist within it. A structure stretching 4 billion light years across is not just large compared to galaxies. It occupies a noticeable fraction of the observable universe. Yet even Quipu is only one region among many in the cosmic web. This layered hierarchy, stars inside galaxies, galaxies inside clusters, clusters inside filaments, and filaments woven into immense networks, suggests that the universe is structured at every scale, with patterns repeating in different forms. What once seemed like isolated points of light now resolves into a connected architecture where gravity has shaped matter into a framework spanning billions of years and billions of light years simultaneously. This perspective also changes how time is understood. When we observe Quipu, we are not seeing it as it exists now, because light from its near side and far side left at different moments, the structure appears stretched across hundreds of millions of years of history, meaning that distance itself encodes evolution. Some clusters are seen earlier in their growth, others later. creating a layered record of cosmic development. The universe does not present itself as a static picture, but as overlapping slices of time, and Quipu becomes a reminder that observing large-scale structure is equivalent to reading deep history written across space. In this sense, the cosmic web is not only a map but a chronicle, preserving the slow assembly of matter under gravity. Looking forward, the future of structures like Quipu is shaped by cosmic expansion. Dark energy continues to accelerate the separation between distant regions, gradually weakening gravitational connections across large distances. Clusters within Quipu that are already gravitationally bound will remain linked, but those at the margins may slowly drift apart as expansion stretches the filaments between them. Over tens of billions of years, the cosmic web will become more fragmented, with large structures isolated in expanding voids. The universe will not tear Quipu apart suddenly, but the growth of new connections will slow and eventually cease, leaving the structure as a fossil of an earlier era when gravity still dominated large-scale assembly. In that distant future, observers within one region might see fewer galaxies as others recede beyond the cosmic horizon, making the universe appear emptier over time. Against this backdrop, the scale of human experience becomes extraordinarily small, yet not meaningless. Earth orbits an ordinary star in one galaxy among hundreds of billions. Within one cluster among many, embedded in a filament that is itself part of a structure vastly smaller than Quipu. From this perspective, human history is a brief flicker, lasting only tens of thousands of years compared to billions required to assemble such structure. Yet the same physical processes that shaped Quipu also shaped the atoms in our bodies. Heavy elements forged in stars, spread through galaxies, recycled into new systems, eventually forming planets and living organisms capable of reflection. The hierarchy of cosmic structure extends downward as well as upward, linking the smallest scales of matter to the largest architecture of the universe. Quipu therefore carries a dual implication. It emphasizes the immensity of the universe, revealing distances and timescales far beyond intuition, while also highlighting the continuity between cosmic evolution and our own existence. The same gravity that gathered galaxies into clusters also shaped the environments where stars formed, where planets emerged, and where chemistry became biology. The universe is not a collection of disconnected pieces, but a continuous process unfolding across scales, with Quipu representing one of the largest patterns that process has produced so far. In recognizing it, we are not stepping outside the universe to observe it. We are part of the same structure composed of matter that has moved through galaxies, clusters, and filaments over billions of years before briefly assembling into conscious observers capable of understanding the scale surrounding them.